All right, everyone, grab your seats and settle in, because today I am absolutely thrilled to be taking you on what I honestly consider to be the ultimate cosmic field trip. I'll be your science teacher for this explainer, and we are embarking on a virtual journey that starts right here on Earth and goes all the way out to the very edge of the universe. We're going to be tracking the path of a small, silent traveler, Voyager 1. Now, you might be thinking this is just a history lesson about old technology, but it's not. It is an incredible story about the farthest reaches of human curiosity. Okay, let's dive into this. Think of this as our class syllabus for the day. First, we'll look at how the grand tour begins. Then, Jupiter, magnets, and slingshots. Next up, Saturn and thick atmospheres. After that, crossing the final boundary. And finally, trillions of years away.
So, let's kick things right off with Section 1, The Grand Tour Begins.
Rewinding the clock back to the late 1970s, the sheer ambition of the original launch objectives was just staggering. In 1977, Voyager 1 launched aboard a massive Titan IIIe rocket. And why right then? Well, scientists realized they could capitalize on a ridiculously rare planetary alignment. The outer planets were perfectly positioned so a single spacecraft could visit multiple worlds in one shot. To pull this off, Voyager 1 was packed with an incredible suite of instruments: cameras, spectrometers, magnetometers, and plasmid detectors, all designed to measure the environments and the energetic radiation of the outer solar system. But honestly, perhaps the most poetic piece of the payload was bolted right to the outside: the Golden Record. It's a gold-plated copper disc carrying sounds, images, greetings in dozens of languages, and a map of nearby pulsars showing exactly where our home is. From day one, my friends, there was absolutely no return ticket planned. Voyager 1 was built to survive the vacuum of space, do its job, and just keep going as long as physics allows.
Moving right along to Section 2, Jupiter, magnets, and slingshots. Teacher time out here. As our field trip reaches the turbulent world of Jupiter, some really incredible physics starts happening, so we need to unpack this. Let's look at a crucial definition on our chalkboard: a magnetosphere. This is the region of space surrounding a planet where its magnetic field completely dominates and traps charged particles. And let me tell you, Jupiter is an absolute monster when it comes to this. And this brilliantly illustrates what that looks like. Jupiter's magnetosphere acts like both an invisible shield and a massive particle trap. Think of it like a giant invisible spiderweb made entirely of magnetic force. High-energy particles from the sun fly in, and this magnetic web catches them, creating radiation belts around Jupiter that are incredibly intense. It essentially creates a massive hazard zone in space. When Voyager actually flew through it, her instruments were measuring an environment harsh enough to completely fry normal electronics. It is literally a miracle of engineering that she survived to tell the tale. Okay, direct your attention to the next crucial term for today: gravity assist. Simply put, this is a maneuver that uses the relative movement and gravity of a planet to alter the path and speed of a spacecraft. Voyager desperately needed this boost to keep our momentum going out toward the darkness.
So how does this ultimate cosmic slingshot actually work? Well, imagine you're on a skateboard, right? Just rolling down the street. Now, a massive, heavy truck is driving past you. If you reach out and grab the side of that moving truck for just a couple of seconds, you are going to steal a tiny fraction of that truck's momentum, and it is going to yank you forward, giving you a massive speed boost before you let go. The crazy thing is, that truck doesn't even notice you were there. That is exactly what Voyager did to Jupiter. She used Jupiter's gravity to grab onto the planet's orbital momentum, stealing a tiny fraction of Jupiter's energy to slingshot herself outward at absolutely incredible speeds.
Which brings us to Section 3, Saturn and thick atmospheres.
Thanks to that massive Jupiter slingshot, our field trip zooms outward to the ring giant. Voyager 1 revealed some incredible structures in Saturn's water ice rings, but the real target here was Saturn's massive moon, Titan. Titan is actually larger than the planet Mercury, and it is the only moon in our entire solar system wrapped in an atmosphere so dense that it completely hides its surface. We're talking surface pressure about 1.5 times what we feel here on Earth. It's dominated by nitrogen and methane. So why does this matter? Because an atmosphere this thick is chemistry in motion. Sunlight and radiation are constantly breaking apart molecules and turning them into complex hydrocarbons, creating mysterious hazes and rains in the freezing cold of the outer solar system. Voyager passed Titan at very close range, which was a move that permanently bent her path upward and completely out of the planetary plane.
Time for Section 4, Crossing the Final Boundary.
Now the pace of our journey shifts a bit as we leave the planets behind. In 1990, at nearly 6 billion kilometers away, Voyager turned her cameras back toward the inner solar system one last time to take a family portrait. Earth appeared as just a tiny point of light, the famous pale blue dot. Every human story, every war, every dream compressed into a single pixel suspended in a sunbeam. It's really profound to think about. After taking that photo, engineers shut her cameras down forever just to save power. Blinded, but pushing forward at 17 kilometers per second, she aimed straight for the dark.
And this brings us to her greatest milestone, the Heliopause checkpoint. This right here is the final boundary of our sun's influence. On side A, you have the pressure of the solar wind pushing outward. On side B, you have the pressure of the interstellar medium, the space between stars, pushing inward. Now when you cross it, there's no signpost floating in space. Voyager couldn't actually see it, she could only feel it. In August 2012, her detectors registered a sharp drop in solar particles and a sudden, massive spike in cosmic rays hitting her from deep space. And that was the moment we knew. Voyager 1 had officially entered interstellar space.
Which leads us to our final stop, Section 5, trillions of years away.
So, Voyager's power source is slowly failing. She won't appear to die to us, she will simply stop answering our calls. Let's walk through this mind-bending timeline of her deep future together. By late 2026, Voyager will be one full light day away from Earth, meaning if you send a message, it takes 24 whole hours to reach her and 24 hours to hear back. Fast forward 40,000 years, long after her radio is dead and humanity might have totally forgotten her, she will pass near the star Gliese 445. Jump ahead to 3 to 4 billion years from now, the Andromeda Galaxy will actually collide with our Milky Way. Gravity is going to completely reshape the sky, and silent little Voyager will just be drifting through a spectacular galactic merger. Jump ahead to 10 trillion years, 1,000 times the current age of the universe. The familiar bright stars are all gone. Only tiny red dwarfs remain. The universe becomes incredibly quiet and dark. Eventually, in a theoretical future, matter itself might break down through proton decay. The universe itself might just slowly erase her atoms.
It's just an incredible thought, isn't it? A machine built back in the 1970s, outliving the very stars that warm us today. It leaves us with this final haunting question on the chalkboard. When the stars fade, will anyone be left to know that life looked up and reached out? Thank you all so much for joining me on this incredible field trip today. I hope you enjoyed this explainer, and remember, keep looking up.